Yes, thank you, Lenny. Yes, I will talk about the initiatives and the research group that I'm leading. And then I will then go to the main focus of the presentation today, which is one of the journal papers that I published last year, which is, I think, my favorite of the papers that I published last year. So you will see some ideas here on resilience, sustainability metrics. You will see bridge engineering. The reason I'm using bridges is because when I was doing my PhD, my focus was bridge engineering. I was trained as a structural engineer. I remember back in the day, I was reading many papers from BOSA because BOSA was publishing in bridge earthquake engineering a lot. So yes, I was trained with SAP 2000, OpenSeas, and all these tools on earthquake engineering. But then I moved to the UK in 2012, and obviously the UK is not an earthquake-prone area. There was zero interest in earthquake engineering, maybe a little bit of interest on dynamics, but again, there was no funding in this area, let alone bridges, because bridges, most of the managers, the ways they see bridges is, a headache. How do we retrofit existing ones? They need money, they need investment. And hence, in terms of research, there's not much. There's not a lot of money in this area either. So I had to transit to go to other areas. So I started thinking about risks, hazards, and I will show you an example of how these ideas were used. So as Eleni mentioned before, I'm currently associate professor at the University of Birmingham. You can scan this if you want to see more on the Meta Infrastructure Group. And the reason I'm here is indeed part of a European grant, which I prepared a couple of years ago, the Recharge project, which is focusing on the optimization of resilience and sustainability using digital technologies. So what is the Recharge project about? The Recharge project is looking at transport, energy assets, and from a systemic point of view, we try to understand their interdependence with lifelines, as well as critical assets, such as bridges, tunnels, roads, etc. That's the title of the project. This is our logo. It's funded by the European Union, the Horizon. It's a Marie Skłodowska-Curie staff exchanges. So if you're researchers, you might want to consider this as a good way to network with other researchers across Europe. But we also received funding from our national guarantee schemes. In the UK, we have the UKRI, the UK Research and Innovation Fund, and in Switzerland, there is the equivalent of the guarantee scheme. I think it's called SERI, right? So what we do, so this project has two components. One component is looking at case study driven resilience and sustainability modeling. So how can you optimize resilience sustainability metrics after a flood, after excessive, aging effects, after earthquakes, as well as a very much educational component, in which case we have been developing, for example, a massive open online course. Do you know what is a massive open online course? Yes, it's like a platform, an electronic platform that includes lectures, tests, videos, and they inform the people who are attending these, who take this massive open online courses. They inform them around a very specific research topic or teaching topic. It could be. So the massive open online course that we are currently developing, hopefully this will be prepared. This will be ready by the end of this year. Will be focusing on critical infrastructure resilience and sustainability modeling. Now, a little bit around my research initiatives. The first one, for which I'm particularly proud of, is the Bridge Ukraine. BridgeUkraine.org is an organization that currently has 45 people. We are representing both men and women from Ukraine. So More than half of these people are Ukrainians. They're engineers, they're policymakers, we have representatives from the government, but we also have consultants, academics from across the world, a lot of people from the UK, but we also have people from Brazil, Philippines, all the way down to Australia. So what we're trying to achieve here is we're trying to understand how the funding goes, how external donors facilitate reconstruction in war-torn countries, because Ukraine has experienced an extensive destruction of its infrastructure, and we need to find ways to build back better. And building back better does not necessarily mean building back stronger structures, but also more flexible systems, systems that are more resilient, okay? As well as complying to and aligned to the European standards for reconstruction. So making structures more sustainable, use less materials, or maybe, reuse materials from rubble, from, existing structures that have been damaged in Ukraine. So what we have done with Bridge Ukraine, we have now recruited 4 professors from leading Ukrainian universities. All of them are developing frameworks. So one of them is a professor on AI and machine learning. They're developing frameworks using data analytics from Ukraine. Another one is focusing on bridges. There's another professor from the Lviv Polytechnic University who is looking at the sustainability of Ukrainian buildings and also liaising with architects in the UK and Ukraine. And they are developing frameworks for reconstructing buildings. I'm just going to give you an example. The buildings that have been damaged in Ukraine will not be reconstructed the same way, okay? Because, for example, the Ukrainians don't want to see their infrastructure being reconstructed the same way that was constructed by the Russians, okay? So they want to see something more European. That means that the role of the engineer is not only to provide all the technical details of the design. So it's not only about materials making the structures compliant to Eurocodes, but also to understand what the policymakers want, what the local people want, as well as what the funders are happy to fund. Imagine the European Investment Bank, for example, they would not fund any project. They would not fund projects that the Ukrainian government would like to see on. They would like for the new constructions to comply to new rules. The meta infrastructure is my research group. So if you go to the website, you will see all the people that are working in different areas, all of them focusing, I would say, pretty much on resilience, sustainability of the built environment, systems, networks. A couple of them are working on machine learning, as well as the new Bauhaus. So we do have one European project now, which is looking at how to optimize architectural designs in terms of materials, operation services to minimize the consumption of energy inside buildings. And we're using digital twins. So we instrument 2 demonstrators at the University of Birmingham. And from that, we are trying to minimize both the energy during construction, but also the energy during operation. That's pretty much what we are doing. Including contribution to the reconstruction in Nepal. This is a small charity that constructs infrastructure in Nepal, and a number of consultants that we have done for the World Bank, the United Nations, the CDRI, as well as presence of my research group on BBC and other channels. So yes, this is the funding of the group. So we started with, I'm just presenting this for the young academics to see what is the route for going to larger grants and more complex grants. So I started from very small grants when I started my career. These were mainly fellowships, small, seed funding, internal funding from the university, to then gradually start attracting as COI and then as PI, larger European grants, UKRI funding, and so on and so forth. So my recommendation as an academic would be to start small, but also visualize something bigger for the future. So when you're building your research areas, try to think, what is the area that you would really like to establish yourselves in? What would you like to become? And what are the steps that you see in the future in order for you to establish yourselves in a particular area? Have I been asked back in my career, what would you like to be? I would potentially say a good bridge engineer. What I'm doing now is, the way I presented at least, is mainly resilience sustainability. But if you see, all my case studies are around bridges. So I'm still doing bridge engineering to some extent, but most of it is coming from different angles, if that makes sense. Just one slide for the University of Birmingham. I don't know how many of you have visited Birmingham. Have you? Has anyone visited Birmingham? No? I have. You did? Yes. It's a very exotic city. We have marvelous weather. Well, that's a joke, obviously. It's 1.5 hours north of London. The weather, I would say, is pretty much like in Switzerland. But what we do have is one of the most beautiful campuses in the UK, the second biggest university. It's a leading university in the UK, especially in engineering. We are leading department, one of the top 10 departments. And we are very well known for producing income. So we're good at receiving funding. In engineering, we also have a fantastic sustainable building, which is a RICS awarded building. And something that is very distinctive, something that characterizes the engineering school, is the National Buried Infrastructure Facility. We have the largest pit in the world. So here we are testing geostructures, okay, buried pipelines and buried infrastructure foundations. And we can test them in large scale. We can do static loading. We can do testing for settlements, dynamic loads, pretty much anything around geostructures. But we also use this lab for structures testing. Right. Now, this is not the first visit of mine at ETH. I've been here back in 2019. The difference that you may see between these photographs and now is me aging. So it's the known aging effect since the last 5 years. But back in the day, I enjoyed delivering a talk around risk and resilience, and that was on bridges and networks exposed to multiple hazards. So that was the time that a lot of researchers were working around the areas of multiple hazards. And that's because both the insurers, the industrialists, but as well as the European Union realized that hazards are not single, they're not alone, okay? So when you're designing a bridge, a network, a facility, a nuclear power plant, it is very likely that this infrastructure will undergo serious stresses, not only because of an earthquake or a flood, but it might be a combination of things. So remember, for example, what happened in Fukushima in Japan, but we also have many, many examples where you had an earthquake initially, and then you had a tsunami, you had scoured foundations, and so on and so forth. So it seems that most of the structures, and especially the critical ones, we do have to consider not only one hazard, but in many occasions, we will have to consider black swan events, high intensity, low probability events that we don't even have in our codes nowadays. A very recent example is the Baltimore Bridge. Okay, you have seen what happened in Baltimore. I mean, the bridge itself, the cost of the bridge itself should not be that high. It should be of the order of a few tens of millions of dollars, right? Because it's an old bridge. What is the value of a 50-year-old bridge? But if you see the consequences of this bridge failure from a systemic point of view, you will realize that the actual losses were multiple times higher than the actual loss of the physical loss of the asset itself. So that gives us a lesson as engineers that no matter how well you design your structure, this structure might experience an extreme shock in the future that might lead to failure. And that failure itself does not give you the actual loss, okay? Because the engineer, the first thing I did when I saw the bridge failure was to calculate the potential cost of the bridge. But if you see the consequences, the indirect losses as a result of this failure, you will have to multiply this by 30 or 50 times in some occasions. And that's because the port was closed after the bridge was in the water. And as a result, the ships could not enter the port. So there were like a huge disruption in operations and transfer of goods. Right. So from a structures point of view and from a network point of view, which are like different angles of the same problem, there is a requirement to make our structures more robust, right? So in your opinion, do we have in Eurocodes any recommendations or any prescriptions, any requirements around resilience? I mean, who considers themselves a structural engineer? Who has used Eurocode to Eurocode 3 in the past? Yeah, have you seen anything around resilience, even in the new versions of Eurocodes? Not so much. I mean, there is a mention in that says, for example, when a bridge fails, you have to put mechanisms in place so that the bridge recovers quickly, or you need to make the failure controllable. Okay, so you need to control the way the structure will fail so that you avoid loss of lives, for example, but not necessarily to recover quickly. And so the notion of resilience is relatively new, well, in engineering at least, because in economics, it started back in the 70s when they were stress testing the banking system. But in engineering, it is a term that has very, very different approach in terms of when we're looking at different tiers. If we look at the structural component, the structural resilience is something different. If you go to the asset level, imagine a bridge, resilience against is different in the sense that in bridges, you have to have mechanisms to replace beams or columns or find ways to restore your foundation quickly. But this is infinitesimal, I would say, when you're looking at the resilience of the system, like the road network. If a bridge fails, you should have some redundancy in the network, meaning that you should have alternative routes, right? So imagine that as a systems of systems approach where you don't only have the road system, but you also have the energy system, and the failure of one system propagates to the other. So the main challenge here is there is different people dealing with the design of a structure, the design of the road network, and the design of the energy network. And there is not much communication between these stakeholders. So going back to the asset level, we will talk about bridges. One of the main challenges is to optimize climate resilience. So make your structure, design your structure in a way that it will be able to recover quickly after a flood or after an earthquake. At the same time, make sure that when you reconstruct this bridge, that the means and the measures that you put in place are sustainable. And what is sustainable? This is such a huge umbrella of terms, sustainability, right? So if you look at the three pillars of sustainability, that means to make it more environmentally friendly, more acceptable by the society, and more, emit less greenhouse gases to the environment. So you can use this as metrics for sustainability, and we will see what sort of metrics we can use for resilience. Now, what is the gap in the knowledge? We usually don't see designers, or we haven't seen many research papers either around the area of optimization, how to optimize resilience sustainability. And again, as I said, as we will not optimize sustainability from all points of view, we'll try to optimize some of the metrics. And we have not consolidated this in our current research and practice in infrastructure adaptation. So the novel solution, the novel proposal in this paper was to integrate resilience sustainability metrics using low carbon infrastructure restoration strategies. So that's essentially greener materials. Now, just a very brief introduction to resilience and sustainability and the correlations between those two. So there is some research that sort of confuse those two terms. They believe that if you make something more resilient, it will automatically be more sustainable, but this is not true. And I will explain this. So Based on this paper by Linkoff et al., sustainability and resilience can be negatively correlated, could be uncorrelated or positively correlated. Okay, what does this mean? So that's a very simple graph to like illustrate this negative, positive, and neutral, if you like, interactions between sustainability and resilience. So there is cases where resilience increases, but sustainability reduces. So that's negative correlation. You have cases where the change in one metric does not really influence the other metric or principle, if you like. And there is positive correlation where you increase the resilience and you improve sustainability metrics at the same time. Very briefly, some examples. Negative correlation. Restoring a bridge leads to CO2 emissions, but increases resilience. So on the one hand, you improve resilience, but you make sustainability worse. But at the same time, you also have benefits to the economy. So from economic point of view, that improves sustainability, right? Because you increase the capacity of the network and so on and so forth. That's just an example. Now, an example of uncorrelated mitigation measures is the case where you restore a bridge with different techniques. In which case, for example, if you use riprap, that's a more sustainable solution because you just use stones as opposed to using, for example, concrete. And that's exactly what we did in this case study that I will show. So that's less sustainable, but irrespective of whether you're using this or this, your resilience is not really influenced because if you look at the network level, the resilience of the network has not been affected, right? Because you strengthen your structure either this way or this way, and you end up having the same capacity, at least theoretically based on if you design the structure, for example, based on Eurocode 2 or Eurocode 3, right? So you assume that the level of safety that you provide is identical. Now, there is a case where you have positive correlations. You strengthen with vegetation an embankment, a backfill, and you, on the one hand, make the embankment stronger, so you improve its resilience, and at the same time, you make it greener, you absorb CO2, and that improves sustainability. And at the same time, it's more acceptable by the society. So, but on the other hand, it does cost money, right? And we don't know in terms of duration how long these measures will be in place because there is other effects affecting its stability. Now, this is the framework of the paper. I will try to explain very briefly the main idea, the central idea of this flowchart. So the idea is in order to optimize resilience sustainability, and I will start from the end, you will need some metrics, as I said before. For example, the metric for sustainability could be CO2 emissions. So this is the tons of CO2 emissions equivalent and resilience. And you will have to find the optimal solutions. So how can you find optimal solutions? You can use, for example, Pareto fronts or MATIC criteria decision-making processes to optimize 2 or 3 parameters depending on what you would like to achieve. So that will help you to make a decision, right? But in order to come up with these metrics, you will need what? You will need to calculate the resilience of your system for a given hazard, as well as your CO2 emissions. Now, going back, how do we calculate resilience? You will need 2 things to calculate resilience. One is the fragility of your asset to a given hazard, and the second one is the asset recovery. So you would need the restoration curves. Now, for the restoration curves, you should consider both the structural capacity gain, which means that how stronger your structure becomes when you add concrete, when you strengthen the foundations, when you add external FRPs or external pre-stressing for a bridge, as well as the reinstatement of your service, which is the traffic. Now, one would think, well, if I strengthen my bridge, in parallel, I'm also increasing the traffic capacity of the road. But this is not really true, because I can think of many cases where when you are actually retrofitting your bridge, the traffic is 0. You would not allow any traffic on the bridge. Or you apply, for example, external pre-stressing, which means you increase the capacity by 50%. I'm just giving you a random estimate here. 50% increase in the capacity of the deck, but at the same time, the traffic is unaffected. So those two, there is some correlation between those two, but you know, for this one, you will have to ask the policymakers or the operators, the people who operate highways, what happens when you strengthen a bridge. This one is more straightforward in the sense that it's more technical, so you know how much strength you gain by applying X, Y, Z measures on the bridge. So that's I would say, it includes technical, but also, you know, policy and decision making. So it's you know, the uncertainty here is greater than this one here, which is a fragility curve. Is anyone familiar with fragility curves? Do you know what fragility curves show? What is the value of fragility curve? So fragility curves gives you the exceedance probability for a given intensity measure. I'm not going to explain here what is the way to extract fragility curves, but mainly the value of the fragility curves. I'm giving you an example. If this is a water charge of, let's say, 10 millimeters per hour, you can calculate the exceedance probability for different conditions of the asset. Here we have deteriorated asset, and here we have the as-built asset. So for the same intensity measure, you will see that you will have, for example, an exceedance probability, which means a failure at different levels of failure. So that the blue line could be a minor, moderate, excessive, a complete damage, all the way down to failure, which is the red line. You have a probability of, let's say here, 90% to have a complete damage, 95% to have extensive damage, or 98% to have a minor damage. So, but that means that we take a probabilistic consideration for the estimation of the damage, because that means that for a given intensity measure, you don't have a deterministic damage, right? You have to consider probabilities of having minor, moderate, excessive, and complete. And at the end of the day, what we do is that we take the sum of these probabilities to calculate the fragility and the potential loss of the asset. So, long story short, in order to calculate your resilience curve, you will need fragility modeling, you will need restoration modeling to extract this curve here. And for the CO2 emissions, which is the metric that we used here for sustainability, you will need to determine from the very beginning what are the stages, what are the modules that you consider. So will you consider from cradle to grave? Will you consider from cradle to cradle? Because there is the whole circle in sustainability, right? So it really depends on the time window that you are looking at. Very briefly, the first module, the product is A1 to A3, for example. That includes mainly the materials, you know, raw materials, extraction, transportation, and manufacturing. The second one is the construction, and that includes transportation of the material, construction and installation processes. So that's what we consider in this framework from cradle to practical completion of the project, right? So which is the implementation of the restoration measures. We did not consider for this particular paper the additional CO2 that would be the result of traffic rerouting, pavement degradation, change in travel behaviors, and all that, because these are the indirect ones, and it's much more difficult to determine. Now, what happens here is I have three maps of how these two metrics evolve with time for three cases. One case is the baseline scenario, and I will show you another two cases with proactive adaptation, which means I do something before the flood, I do something before the hazard happens, so I can strengthen my asset to minimize losses in the future. And the other scenario is we're doing that reactively. We're doing that in the sense that, you know, the hazard occurs first, you have the damage, and then you go on site to repair. So it's like a repair scenario. The baseline scenario says, that's the easy way to read this diagram here, the resilience curve. You have an asset at the beginning of its at the completion of its construction, it has 100% functionality. With time, its functionality reduces, and then it drops when you have a hazard. What you do as an engineer afterwards is that you have a small lag time and you bounce back to the original functionality after you do the repair. That means that you have upfront and ancillary CO2. Upfront are the direct ones relating to the material. ancillary is the indirect ones. So what you see here is you have an increase of CO2 emissions. That's the cumulative CO2 emissions. This is the structure itself. This is the traffic. So that's the the CO2 emissions that you have if you experience a hazard like this that leads to the loss of the performance of the asset. Now, see what would happen at two different scenarios now. And we have quantified these scenarios. What happens if you have proactive adaptation, which means just follow the concept here. You have maintenance here. At point B, you decide that you need to do something on the structure, so strengthen the structure and go back to the original. And you do that quite frequently. You see every 2 years or every 6 years, depending on the frequency of inspections. So that means that you keep very close to the baseline, to the initial capacity of your structure by doing small tweaks throughout the life of the asset. And that leads to a very controllable CO2 emission pattern, because you make a wise use and application of materials, because you can plan ahead. Now, what happens if you do that after the threat, after the flood happens, after the earthquake? Then you have a pretty much uncontrollable case where your structure is severely damaged because you have already lost part of your strength here, and the additional loss of strength is unpredicted here. So you have now a severe loss of your structure, a severe loss of your structural capacity. And then you obviously have to decide whether you're going back to the original functionality, go back to higher capacity, because your traffic loads have been increased. And by comparing as well the areas under these two graphs, you will see that the area under this graph is obviously much smaller than the area of this graph. And the area under this graph is what we call resilience index. So very quickly, you can see that obviously it is much better to invest proactively before anything happens for the infrastructure, rather than investing reactively after your earthquake happens or after your flood happens. Now the question is, why don't we do that then? Any ideas?
Cost.
It's the cost, because the operator has an X amount of money to spend per year. And what do they usually do is like a firefighting strategy. We invest a little bit here and there wherever the need is very, very obvious. You will not going to go to an intact bridge like the Baltimore Bridge and say, okay, let's make this structure more robust. It is very rare that you would do that. But the intelligent way to invest in infrastructure is to do it proactively. Because as we all know, if you proactively protect your health, if you proactively do something for your car, it is very likely that you will lose less in the future. Now, so what we did is that we weighted the CO2 emissions and the resilience index based on the different potential levels of damage for given scenarios of floods. So this is very briefly the steps that we followed. We calculated the hazard curve. We calculated the vulnerability curves for a reference bridge, a 3-span bridge. We then calculated the restoration and reinstatement models. There is another paper. I can share this presentation with you to see how we modeled the restoration curves. Then we calculated the whole life carbon emissions, and the impact assessments followed the IPCC approach. And from that, we calculated CO2 emissions for different restoration strategies. The capacity of the structure has been increased probabilistically. So we assumed 4 damage states. That's what you see here, the probability for being at a given damage state. And then we calculated based on these different scenarios, the resilience index, the CO2 emissions, the metric of sustainability, in which case was the inverse of the CO2 emissions. So it was CO2 emissions for a given measure over the total over the max CO2 emissions. And we also considered the cost metric. So we assumed a resilience, we consider a resilience metric, sustainability metric, and a cost metric. So how do you make sense of all that? Well, the answer is, as I said, there is many different ways to do that, but in my opinion, the easiest way to present it to an operator is to tell them, look, I can give you a global metric, which will represent all these three metrics. And you can decide as an operator how to tweak these metrics, which is more important for you. Is it the sustainability, so to reduce CO2? Is it the resilience, or is it the cost? And then you can tweak that by using the gamma factors, what you see here as gamma S, gamma R, and gamma C, to make sense of the global metrics, to see how much each solution influences your final design. So very briefly, we applied this on a real bridge, a 3-span bridge. This is a very typical case. So whoever is the bridge engineer here knows that this is pretty much the average size, the average height of a bridge. This is a river crossing bridge. It has a total length of approximately 101 meters. It has a continuous box girder deck on bearings. And what we assumed here as a hazard, as the main hazard to demonstrate the applicability of this methodology, was to assume that you have scour at the foundation due to flooding. So something like this. This is quite, just to make it more, just to illustrate it with something more practical, something more realistic. So what we have done for this particular bridge, we have developed the fragility curves, as I said before, and the restoration curves to calculate the resilience indexes. So we have done this for, how did we do this? We analyzed the bridge in Plaxis for different scour scenarios. And for these scour scenarios, we calculated potential change in the bending moments. We assumed a number of different metrics, bending moments, settlements, so a number of different structural, what we call engineering demand parameters to monitor throughout the analysis the evolution of these metrics. So based on that, we came up with these fragility curves. I do have a couple of papers where in which you can read to see step by step how to calculate these fragility curves. These are the restoration models from the paper that I mentioned before. And how did we come up with this graph here? You will see something like this in the paper. This is like a map of different tasks. So what we did, we reached out to operators and consultants, and we asked them, if you have a bridge like this that has this settlement, this cracking, these structural defects after a flood, and this is like a minor, moderate, excessive, or complete damage. So we showed them 4 different illustrations of the same bridge. What are the tasks that you need to follow, and what is the sequence of these tasks? So we came up with this strategy of restoration strategies for different levels of damage. And what we also did is that we have then calculated for each one of these tasks, because these are the tasks that is on the left-hand side, the first column, these 19 tasks, and we calculated quantities of materials. So these are CO2 emissions for the materials, for the on-site activities, and for the transportation of materials. This is the total CO2 emissions per task. This is the change in the CO2 emissions if you use green methods. And I say methods because that includes materials, but also transfer of goods. So you can use, for example, fuel that produces less CO2. And we also took into account the CO2 tax, because well, this is going to be something that will, in my opinion, transform the future of sustainable structural solutions, is what we call the CO2 tax. You will see that the most advanced countries, technologically advanced countries, they started putting some really high CO2 tax. And the reason is that companies that are, constructing, they will have to give back to the people, to improve the condition of the environment, because they emit a lot of CO2 to the environment. Anyway, and we also saw what was the impact of each one of these tasks when we considered greener solutions. So that is the influence on the duration. So some green solutions might have made things a bit slower, but overall you will see that green solutions were by far better than the conventional gray solutions of conventional concrete. So what we have seen here in the first figure that you see on the left-hand side is that despite the increase in the cost of the greener solutions, up to 20%, because, for example, nowadays we know that green concrete, for example, is more expensive than traditional concrete. So despite this, I would say, quite important difference in the cost of greener solutions, the low carbon restoration strategy led to an overall of 50 to 60% reduction of the total CO2. And that's, in my opinion, a clear incentive in adopting greener solutions. So overall, you know, the normalized CO2, these are the green solutions, this is the conventional solutions. In all cases examined here, constantly, the greener solutions gave us better results in terms of normalized CO2. The other thing that we also observed which we can see in the second figure, is that generally, and that's the global metric that I mentioned before. Okay, so we are showing in the x-axis the global metric that takes into account sustainability metric, resilience metric, and cost metric, and that's the annual probability of exceedance for the hazard, so in which case is the flood. And we assumed here 3 different peak flows. This is the current peak flow, the one that we measure nowadays in our rivers. Okay, this is the current peak flow, and then we consider some increases to consider, for example, some climate projections. What would happen if you had 10, 25, and 50% increase in your annual peak flow? The result of that showed that the metrics of resilience, sustainability, and cost take values between, obviously, as we understand, between 0 and 1. So for more frequent events, we found that the events are characterized by annual probability, say, larger than 1. So for these events here, there seems to be a dramatic reduction in the ISRC, the global metric of ISRC. And that means that more resilient measures are needed to be urgently taken for critical infrastructure, especially for quite frequent events. So that makes the argument, in my opinion, for proactive adaptation. That you know, by showing this graph to an operator, if that bridge was a real bridge in their network that was crossing a river, you can very easily here make the argument that put some money on the structure now to avoid a loss of losses in the future. That will, at the same time, increase your resilience and your sustainability. Okay, so that's, in my opinion, an illustrative way of showing the value of this methodology. Now, before I finish, I have a couple more slides. I very recently went to a conference of the ECTP, the European Construction and Technology and Policy Conference, where they were discussing the gaps in delivering more resilient infrastructure. So one of the things that we discussed there, and perhaps I will open the floor to some of you to interact with me or give me some answers, some ideas, and that what I have here is that in order to quantify resilience, it is important to first assess the risks. However, it appears that we are addressing currently either high intensity, low probability risks that may develop or risks that may develop in the medium to long term, which increases uncertainty and weakens our commitment to resilience. So the question is, in simple words, if we understand, if we admit that the uncertainty is so severe to consider climate projections to design our infrastructure, how are we going to do it? How are we going to increase the resilience of our systems if we are unsure of what is happening within the next 20, 30, 50 years? Because we are designing our infrastructure for, in some occasions, for 120 or even 500 years, if we're talking about a bridge or a nuclear power plant. So in your opinion, how are we going to do it if the uncertainty is so severe? Any ideas? Do we have any tools in place to design? Are we just going to over-design everything, or the online people can also interact if they want to. So one way is obviously to say, okay, we're going to analyze for the maximum scenarios, the minimum scenarios for climate projections, and then see where we are. But you will see that even if there is more than 50 climate projection models now, okay, for different hazards out there, and you will see that these 50 models are very far off each other. So even if you say, okay, I will do it, you still have a huge discrepancy by comparing the models. So one way to do it is to spot check, right? So analyze for a very high hazard, which introduces us to the idea of stress testing. Does anyone know what is stress testing? No? Well, we are doing that in the banking system. So we sort of impose a stressor and we see what is the result of that. So we can analyze our structures for, assume very extreme events in the future. And stress testing can refer not only to the hazard, so assume a very strong precipitation event, or a very strong earthquake, or a very large explosion. But you can also consider stress testing at different stages of resilience quantification. For example, we spoke about restoration. And restoration means that we need materials, we need the finances in place, we need the people, the labor, we need equipment, we need to transfer materials, and so on and so forth. So stress testing could consider, for example, minimum access to the infrastructure after an event. So that's stress testing. So instead of, having to deal with an extremely wide analysis of infrastructure for different climate projections, and again, there is severe uncertainty there, we might want to consider a number of potential events, but that's where you need the operators to tell you what is the sort of events that they dealt with in the past, and sort of increase the intensity of these events. What is the sort of lack of labor or lack of materials that they had after an event, and try to strengthen these points in the system. So stress testing will highlight what are the weaknesses of the system and potentially make us, increase our confidence in making decisions for climate projections. And I'm currently working in what we call a threat agnostic restoration and adaptation strategies, which means that you don't really know what will happen, but you're trying to assume that your system loses one of the critical links, a bridge, a tunnel, a junction. What would happen after that? And in my opinion, this is the way forward for interdependent infrastructure, where we increase the demand without really looking at the system. So we have to start doing that. I think that if they had done stress testing in the port in Baltimore, they wouldn't have the problem with the bridge now. It took them 1 month to remove the bridge. And of course, that goes back to what I mentioned at the beginning of my lecture today about the role of inclusive design. So when you're designing the Baltimore Bridge in a few months from now, you should not do it as an engineer, like stay in your office and not ask anyone, just assume larger factors of safety. You should also ask the people who are operating the network and the operators of other networks if that serves the purpose, and also run a what if scenarios for your system. And of course, be quantitative is very important because that means that you can actually show to the operators a number and tell them this is better than this one, so they can very quickly understand and justify their investments. I think that's the main discussion points. And again, this goes back to the tiered approach of what the policy understands, what the risk assessors understand, and what we understand as engineers. And I put myself in the engineers side of things. So in conclusion, I hope the takeaway from the lecture today was that sustainability and resilience are not identical terms and philosophies. There is some overlap, but in some cases they're synergistic, and in some cases they stand independent or even conflicting each other. You can do optimization with different ways, but you can also use something very simplistic, as a global metric for decision making, incorporating different principles. That could be resilience, sustainability, cost, but it can as well include, social acceptance, for example. And across all examined scenarios, the implementation of low carbon restoration strategy was proven to be more beneficial. This strategy can reduce CO2 and can lead to a 50% increase in this global metric that I showed before. That's the output, and that's the list of publications. I will make this available to you. Thank you very much.